posting them. And now we're recording. So let me get the slideshow going. So yeah, I'll be recording all the lectures, posting them. You can go back, revisit them. All of the slides will be available. I'll show you the course website and stuff. It's still a little bit, I need to do some work to get everything linked up correctly, but by the end of the day, it should be all a little bit more streamlined. Right now, it's, you'll see. So last time we talked about computer architecture, kind of like the idea of having these different levels of the memory hierarchy. So you have your CPU, which has direct access to very small amounts of data at any time. You can go out to the system memory, which is fast and medium sized. And then you can go out to your storage disk. And then finally, you have like taking data over the network, downloading it from the internet. And we'll be mainly working with that either in main memory or in the sort of remote sense. I'm also going to close this so we're not bothering people. And one of the main things I talked about at the end on last Friday was this idea that in a lot of earth science applications, we're working with very large data sets, remote sensing, modeling sorts of things, or pulling data from various locations on the internet. And one of the main bottlenecks in computing is, or at least in earth science computing, is this memory bottleneck of we can't get the data to the computer fast enough. So just to sort of set this off, we're talking about parallel computing today, which in the case of, at least as far as I can tell, one of the main things I want to sort of teach you is how to work with processing large amounts of data, which will require parallel computing. I'm not going to be talking about like big numerical PD simulations or climate model, like how to implement a climate model on your own. Because this is, again, we're talking more about working with large data sets rather than trying to crunch a huge amount of numbers. So in that respect, parallel computing is a little bit different from something like these big applications of giant climate models or weather models or things like that. And more about how do we get answers out of our data efficiently rather than setting your computer to do something, waiting overnight for an answer. So with that, I want to, and we don't have to go entirely around the room, but who has like done any sort of parallel computing in their own research? About half. All of your computers at this point probably have multiple cores that you could take advantage of. There's also other resources, UA, HPC, which I should probably do more of a formal thing. Maybe we can talk about that for like 5-10 minutes on Friday. There are other cloud compute platforms that you can use. And then finally, many of you probably will go on to work in situations where you'll have access to something like an NCAR machine or something, a Department of Energy supercomputer where you'll be able to use parallel computing. So there are multiple levels to this, and we'll talk a little bit about that. I think the main thing with parallel computing that you will get out of this class is just familiarity with like how to use it for data processing and pipelining. But this rabbit hole goes much deeper, and you'll see that in a second. So just wanted to revisit this Moore's law figure. So the idea of Moore's law was roughly that the speed of computers roughly doubles, or at least they count it in terms of like transistor numbers every few years. And there are some indications that that's sort of, you could say slowing down or something like that. We'll talk about that a little bit more maybe in one of your homeworks. But the main thing that I wanted to really highlight is this is not like a super uh, old thing that we're going to be talking about. A lot of the tools and stuff are fairly newly developed. So this figure shows from 1970 to approximately now in its log scale on the Y. So computer speeds have gone up, and roughly I would say somewhere in the 2000 to 2004 timeframe was when parallel or multi-core processing computers became like the standard. I still have the computer that I like built in college, roughly 2012, and that's got like 4 cores on it. And that was like a hot new thing at the time, and I spent like way more money than I had to build that. But just to like, that's not too long after the sort of delineation that I've arbitrarily made, and that had like 4 cores. Now most of your laptops probably have somewhere in the 4 to 8 range, but they've grown to take advantage of multiple cores so that you can do more computing, because this sort of trend here could not have held. They could not make the processing units in computers small enough, or continue to shrink them down to be faster, which again is related to the speed of light, which we talked about in the first lecture. So that's really the impetus for going to this multi-core era. It's not necessarily because we wanted to have to make all of our algorithms more complex, but it's more of a fundamental problem of the hardware. Now, the move to this multi-core situation, again, as a necessity, increases complexity. And it wasn't until, I would say, roughly 10, 15 years ago that like your average scientist or engineer could actually make use of this hardware. It was very hard. Like the software implementation to actually do this was very difficult. We'll talk a little bit about some of those difficulties, but at this point in time, tools are good. They're not great, they're good. They'll get better, I hope. But we can actually start to make use of this without you having to be a hardcore computer scientist, right? So that's kind of the thing I wanted to impart here. So if you're not familiar, parallel computing is this idea of taking advantage of doing multiple things at once in parallel. So what we talked about with computer architecture last week was all serial. We talked about, instructions or data is read from memory. They go through the instruction set, they do some compute, and then they output it somewhere. And that was all done sort of in a single line. So that's sort of this, where you have a task, it gets broken down into those instructions that the computer kind of knows how to do, and then it goes through the CPU. So now that we have multi-core machines, essentially you can split your tasks into little chunks that are quote unquote independent. We'll talk about that in a second. And run them at the same time. So you have multiple CPU cores that can each individually do their own thing. Easy peasy. One side note that I wanted to make sure I highlighted. We're talking about parallel computing. There's also this sort of wider field of distributed computing, which is you have your laptop, it has multiple CPU cores. There are these other machines like cloud computing and things where you can have multiple nodes, where storage may be shared, but memory is not, and then each individual node has its own set of CPU processors. So this would be like also a supercomputer, for instance, where when you submit a job, you could have multiple nodes. And we'll see how that sort of can impact things in one of my examples. Does the idea of like multiple nodes versus multiple CPUs sort of, you folks kind of get the idea there? Okay. So this is not something I'm going to quiz you on. It's just something that you probably should be sort of aware of is this idea of Flynn's taxonomy in terms of parallel computing. So what we talked about on last Friday was this upper left corner where you have single instructions that are operating on single data. It's just serial computing. You get one piece of data, you do some operation, you output it. There are also these other ideas that are trading off between multiple data streams or multiple instruction streams. And so this idea of SIMD is something that anyone who's used NumPy, everyone's used NumPy here, right? Yeah, so if you've used NumPy, you've done SIMD computing. This is single instruction, multiple data. So if you add two big arrays together, basically under the hood, what happens is you vectorize the operation, which means that the computer or the CPU is actually much smarter than we've talked about. And it can actually make use of the fact that it is so much faster than the amount of data you can read in. So it can do multiple operations at once. Then there's sort of this other idea that's multiple instructions, single data. This would be when you are doing some sort of like complex operation where, for instance, you need to, if you want to just standardize data, you need to subtract the mean and then divide by the standard deviation. And so if you have a circuitry that's specifically built for that, it can try to do those operations sort of at the same time on the same piece of data. So these are sort of the two specialized variants. You will never be asked to actually implement something like these, but just for your knowledge, they happen under the hood. And then MIMD is kind of what we're going to be talking about more in depth, where you have multiple computers, multiple processors. Your data set is big enough that it won't fit in memory. And this is where like true parallel or distributed computing comes into play. So these happen sort of at the circuitry level that you don't have to worry about. And this is really where we're talking. There is some of that under the hood as well, but again, I don't want to bore you too much with it. It's just a good thing to know. Okay, so when we talk about parallel computing, there are sort of the sort of benchmark that you want to think about is if I scale up my compute, how much faster do I get, right? Like we don't care about adding more processors because we can waste more energy. We want to get more efficient answers from our science questions, right? Like that's the fundamental, like why we do this. And so there are two sort of questions that you can ask as you scale up the size of your compute. And they are known as weak and strong scaling. So the idea of weak scaling is just that you increase both the amount of compute that you have as well as the size of the problem. So in our case, if it's a groundwater flow equation or something like that, you increase the number of grid cells at the same rate that you increase the number of cores. And so ideally, you keep that performance constant, right? You're increasing two things proportionally to each other. Does that kind of make sense? Then the other idea is strong scaling. So this weak scaling addresses the question of how big can I make my problem before I run into computing limitations? Strong scaling, on the other hand, asks the question, how much faster could I compute this? And the idea there is you increase the number of cores while holding the problem size constant. And ideally, right, as you increase your compute, you proportionally decrease linearly the amount of time that it takes for you to solve your problem, right? These both make quite a bit of sense. So where do limitations come in? I have this up on the screen, but like intuitively, these are ideal performances. There's overhead in the computation, right? And so this idea is encapsulated in Amdahl's law. I don't have the formula up on the screen, and I'm not going to ask you for it, but you can go find it. And essentially, what Amdahl's law says is speed up is limited to how much of the problem that you're trying to solve can be actually run in parallel. So that's showing this figure here, where if you can run like 95% of your problem in parallel, you can scale out to a huge number of processors. As that goes down, when it's like 50%, you kind of bottleneck out at like 10 processors or so. And so this just means like what happens is at some point you end up waiting for the non-parallel parts of your algorithm. And when we look at computational graphs, this will become possibly a little bit clearer as to where that could occur. I'd like to pause here and just ask you like to think through like what would cause something to not be able to be run in parallel.
And you have the state in model. For example, in the four column, the state of your model depends on the previous system. So it needs to go in sequence.
Exactly. Yeah. Any other examples? But that's an excellent one. Yeah, the sequential processing where you just need an answer to be able to use it for the next step. Others.
You should give us a hint.
The other one that's a big one is I/O speed, input output. Reading, if you need a new piece of data and your disk is busy loading other data, you just need to wait for it. You can't do anything until you get the data into your memory.
So in that case, like the processing unit just be way quicker than the input output.
Mm-hmm.
So you just be limited by that.
Yep. And that's going to be fundamentally in the last half of the class when we're talking machine learning, almost entirely fundamentally, that's the problem. And we will not be able to solve it, but I'll teach you some tricks to help. So yeah, waiting for data from memory or waiting for data that needs to be used sequentially are sort of the two big operations. So that's really what will limit your scalability. Okay, so I can give you a quick example of this from my own work. I developed this software package called MetSim, and what it does is it takes daily input data of min, max temperature, and precip, and it tries to estimate sub-daily variables for, in addition to temperature and precip, things like shortwave radiation based on like solar geometry and some heuristics about like if it's raining, it's probably cloudy or whatever. And this is really used, the main reason that it was developed and is used is because we don't have a MET station every 1 kilometer. So what you do is you use MET stations you have, but you also take gridded data from weather models or climate models, and then you use this to estimate the other variables that you would need to run like a hydrologic model, for instance. So it is implemented using standard tools, and the reason I say that is because this is the type of stuff that you probably will be using and probably have used. So this is an example of kind of how you can expect scaling to go. The core sort of architecture of the thing is there are 3 steps in this, and they run at like the grid scale. So every location in your gridded domain that gets boxed up can be run independently. They don't depend on each other, right? So there's a high degree of parallelization. So it takes some input. It coordinates with a driver how to distribute the calculations. And then each of the subdomains gets its own little calculation that's run in parallel. And what we see with the strong and weak scaling, again, my figure is a little bit reversed from the previous one I showed, but ideal, you want to be as close to the green line as possible. And what we see when we do strong scaling, so again, same problem size, but adding more and more compute, you kind of see this this curvature and then an evening out as we go from 2 to 128 cores. Can anyone possibly speculate why you see a hinge there? I should also note that this was this figure is from roughly 2019, which may help. No guesses?
Have to do with what we just talked about, those two reasons.
It does.
So you're limited from drawing from storage.
In this case, it's no, that's a very accurate description. So what happens is this this experiment was run on a machine that has its base processor count per node was 16. So once you cross this threshold, you start to go to multiple nodes across the compute architecture, and it can use, so like it starts to get like memory bound here, but then as you go back out, and you would see this again at some point where coordination across the multiple nodes starts to help you because each of them has their own ability to do more basically writing of data to the disk. So right here, it's like you're saturated at that point where all 16 cores are writing to disk, but when you go out to 32, now you've got two separate things that can write the data to separate files. Does that kind of make sense? Yeah. And you don't really see that the same for weak scaling. And again, that's because you're scaling the problem size with the compute size. And this would continue to go up exponentially. And that's because at some point, the problem is you just can't write the output fast enough. Again, here the problem is output writing is the bottleneck, right? Like we're taking daily inputs and we're writing like hourly outputs. So it's 25 times more output intensive than it is input intensive, roughly speaking. It's actually more like 100 times, but so yeah, IO bounds on big data processing algorithms are almost entirely what you're going to be facing. Unless you're like doing something really computationally intensive in terms of like iterative solvers or things like that. But again, we won't be talking about that in this class. Cool. So as I mentioned, you know, the elephant in the room is IO and data storage. So all of the processing stuff that we've talked about, and we did talk about last week, is sort of with this idea of having the data in memory. And we saw sort of with the memory hierarchy, reading data from even like a new SSD solid state disk like your laptops have is, you know, orders of magnitude slower than it is to read from memory that's already loaded in. So in, again, sort of this last 10 years, 15 years, data storage formats have evolved a lot. So I'm sure all of you have worked with something like CSV data. It's text data, right? It's like you can open it up and look at it and read it. I don't quite know where we'll fit it in, but I do want to talk about data encoding at some point. Most text data is stored as this format called UTF-8, which uses 8 bits, I believe, for any character, or 8 bytes. I'll have to do some research. But for any character, it's sort of like a lot of redundant storage in terms of like, if you're only storing numbers, the data is much bigger than you actually need it to be when it's stored on your disk. So that's something that other data formats have evolved to take advantage of, as well as being able to process data in parallel. So there are things like databases, like SQL or whatever, that realistically you might use at some point, but are not going to be the primary data formats that you'll work with. They're more for business purposes and things like that. But that's sort of a separate evolution. So there's sort of an analog to CSV files. One example is called Parquet. These are these data storages that I'm talking about are stored in binary with I'm not going to say proprietary, but custom sort of representations of how the data is stored. And it allows them to be, 10, 20 times smaller than like writing data from disk or as text, sorry. The other thing that a lot of these new file formats have, and it's a little bit hard to see in here, but they use a hierarchical structure. So Parquet, again, is my example of an analog to a CSV. So anything like if you work in Pandas or whatever, you might find a Parquet file, it will open up. It's just a table, but it's arranged in a way that has this idea of chunks. So that one's maybe a little bit more esoteric, but I assume many of you have seen NetCDF. Has anyone not worked with NetCDF before? You have, you took my class.
Okay, well, I guess.
We just didn't talk about it in depth, but.
What do you mean by analog CSV?
Yeah, that's a really good question. I didn't explain that. It's like the idea of the data structure of having rows and columns. So it's like a tabular, they call it tabular data. So it has, named variables as columns and then some row structure that is, either time or locations or something like that.
So Pandas data frames would be kind of in the right-hand column of that, where you might have multiple different variables that are titled, named, and already.
I would
that format.
Anything sort of, but CSV and Parquet are both tabular formats that Pandas is a computational representation of. Yeah. Did that answer your question? Seems no.
Kind of.
Wait, so you said Parquet and NetCDF are computational representations of what Panda does? Wait. Sorry, I think I'm a little lost.
Yeah, I think I've confused multiple of you. CSV and Parquet are data encodings of tabular data. Pandas is a data model that lets you operate on rows and columns of data.
Okay.
So this is like the actual storage format for something like a table, and Pandas is
What allows you to do the computation on the table?
Yeah.
Okay, so then you're saying like CSV and Parquet, so this actually encodes like every single like letter or number inside the entire table, and the CSV does it like really rudimentarily,
yeah.
And then the Parquet does it like within chunks, so it's like okay.
Yeah, so CSV again is something you can like just open up in a text editor and look at. Parquet you can't.
Okay.
Like if you tried to open it with VS Code or Jupyter Notebook, it's just going to be a blob of garbage.
Mm-hmm.
And that's because it has you need to decode the Parquet format according to how they defined it.
Okay.
And again, we'll talk about that a little bit more next week.
Which one is more safer in terms of white corruption? Because sometimes you mess it up with the encoding this CSV.
Which one is more safe in terms of corruption? It depends how sloppy you are at your keyboard, I would say. If you delete a comma from a CSV, it's a problem. It's a little bit more work to mess up a Parquet file in that way.
Is it common to use Parquet these days?
I
never seen in my, I don't know.
It's still somewhat common. There are other tabular formats like Arrow and stuff that are, and again, I don't really work in the Arrow or in the tabular data space too much, which is why I'll focus on these two in a second. But if you're talking about just like regular data corruption of like, oh, I have a deteriorating hard drive or something, then Parquet is probably going to be more likely to be messed up. because it is a compressed, or, you know, it's like its own specific representation of the data.
What about polars? We use because kind of polar. And it has its own proprietary format, which is similar to Spark.
Oh yeah, Spark is another one that's quite popular now. Yeah, I should have actually probably drawn something a little bit more modern, but polars can also work with, polars and pandas are two Python libraries that are for working with tabular data. Polars is newer. I haven't actually played with it too much.
Yes, a bit, but I know that they have their own proprietary format to store the data. Yeah, better than
Yes, so CSV, convenient, but limited. You can't have billions of rows or something because it's going to get too big. It's going to be hard to load it into memory. One of the nice things about some of these proprietary or binary formats is when you open the data, it can be loaded lazily. So this, you need to read everything in the file. Here, you can open this and it has some metadata. And then if you say, give me the 5 millionth row, it won't read all of this. It'll just go down to 5 million and read that part for you.
So when you use FlowPy and you have to get the binary reader, is it stored in like a Parquet sort of ordeal?
It's a USGS, its own format.
Nice.
So there are many formats of data that can come out. Again, we'll talk about this more probably next week. I don't think I'm going to talk about it on Friday. But data representation, again, you know, how do you go from binary, just ones and zeros, to like, whoops, I'm going to punch this TV at some point, to like data that like you can read and has like names, like, you know, precipitation or whatever. Like, how does that happen? So we'll talk about that. The other idea that I just wanted to really, before we run out of time, make sure that we talked about was this idea of multi-dimensional arrays. So this is tabular. Again, it has rows, columns. You can think of that as a, you know, if you strip away all of the headers and the row labels, it's just an array, right? It's just a 2D array, right? So when you go out to more and more dimensions or variables, right? Like the atmosphere, the ocean, the subsurface, it's all 3D in terms of space, but we also have time. So that's where we get into things like NetCDF and Zarr. So NetCDF is super common in earth science. It's also a binary format. We'll talk more about how to work with it later. But the idea is, you know, in this case, they're showing you know, this would be like a surface temperature map, for instance, where every time has a 2-dimensional thing. So this would be like a map for every time step. It can go out to multiple kind of arbitrary number of dimensions, which is hard to think about. And we'll see how that shakes out, especially with machine learning stuff later, because dimensions don't necessarily mean time or space. They're just independent axes. And we will create things with, you know, 4 or 5 dimensions by the end of the class and have them be sensible to you. So NetCDF is one example of this. NetCDF files are, well, NetCDF as a file format is 1 file per data set. You can have multiple data sets, but at the end of the day, it's stored in 1 file. And again, when we're talking about I/O, or, you know, being memory bound, reading from a single file, there are bottlenecks there. So one of the more recent innovations is this idea of chunked data sets, where instead of having 1 file per data set, you have some sort of like overall architecture and then many sub files, which again are all binary. Like you can't just open it up and look at it. But an example of this is Zarr, where, and we'll work with these data sets, so it will come together. But the idea of Zarr is you have some metadata, which is human readable. Like you could go and open up it's called JSON. It's just a type of configuration file. You could go look at it and say like, oh, who made this, or what time was it written at, or what variables are in it. And then all of the individual pieces of data are stored in these chunked binary blobs, essentially. When I say blob, it just means like it's a bunch of storage on your computer that you can't really like look at it unless you decode it using specific software.
So is converting between NetCDF and, for example, ZAR easy, or are they?
It's easy, yeah. With Xarray, the Python library, you can open a NetCDF and write a ZAR, or open a ZAR and write a NetCDF. They have, these data types have their various use cases. So like, it's actually much easier to hand someone else a NetCDF file than it is a ZAR file, because a ZAR file is actually like a bunch of files. So there are trade-offs for sure. And again, if you take like a single, column out of this NetCDF file, you could write it to a CSV, no problem. So it's just dependent on what the dimensions and stuff of your data are.
Mozart has a common driver because NetCDF, depending, you need to use, H5 files or like 3 or 4 different form drivers to open the file.
Yeah, so when I talk about these file formats, they're all like things that people came up with, right? Like they're standards that we agreed upon. We were like, oh, Parquet, that's a good idea. Someone made it, and then people agreed that's a good idea. Anyone could write a piece of software that could decode a Parquet file. And so that does happen with NetCDF. There are like multiple software packages that can decode what's in them. This is getting a little in the weeds. NetCDF is actually like a standard based on another file format, which is based on another file format. So it's not super important, but there are multiple ways to read a NetCDF file. As far as I'm aware, ZAR is designed by committee, and there's only one like sort of main source of how to read ZAR files. There are multiple, for every software language. So if you're reading a ZAR file in Python versus in Rust versus in C++, the actual underlying implementation is different, but they all like do the same thing logically. Does that make sense? Okay. We're about a couple minutes out. So I just want to get through this. Practically speaking, writing parallel software sucks. It's really hard because what happens is you have many tasks, right? We're generally not trying to do like 2 things on the computer. And so you end up with these task graphs that are very convoluted. So like, it's like if I need to do this, then I need these pieces first, and then that gets used over here. There are also like fundamental problems of if you try to do things. This is called a race condition, where you have 2 separate things that you want to compute that share the same internal data. If you do your operations in the wrong order in parallel, you can end up with this race condition where you end up with like data that becomes invalid or corrupted in various ways. Luckily, you don't have to do that. So this is just to say, for all intents and purposes, most parallel computing that you will do is implemented by computer scientists who go, they have worked through like, oh, if this is my data and the algorithm I want to implement, it will come up with the task graph for you and do it. So I'm just saying we're throwing a lot under the rug, and don't worry about it. So we'll primarily be working with this parallelism through Dask. Dask is a Python library that offers pretty high-level integration with things like Xarray, which we'll talk about on Friday. And it does offer you like what I'm going to call low level in our parlance. This is computer scientists would laugh me out of the room, but when I say low level, you can write your algorithms in ways that you say like do this, then this, and this can go in parallel with that. And so we'll talk about that or we'll demo that on Friday and look at how it comes up with task graphs and stuff. And you can see this is like the Dask dashboard. This looks like it has like 16. Each of these little rows is an example of a separate stream of processing. So we'll look at this in real time on Friday. But it makes use of all of your stuff, and it will tell you, like, am I doing something that's a memory operation or a compute operation? And just lets you kind of see granularly how your computing is going. And it will give you an idea, this being so full means that the computer is being well utilized. There's a lot of like empty space, which is often the case. It means that you're mostly waiting around for the computer to do something. So that was the main thing I had. I wanted to highlight this. I'll post this on D2L. Nothing else for those of you who are just joining will be on D2L. It will all be hosted on GitHub. And so I have the course repo, which has set up for code spaces, which I'll show you next time. It also has the website, which is, oh no, I'll try. Oh, we've got 3 minutes. I can maybe do a code space demo. I actually don't know if we'll get enough time. So this is the course website. Eventually it will be filled out. I have, again, the lectures are posted, but they're not linked yet. So I just need to update the links. It was still processing while I was getting ready for today. But one of the things I do want to highlight, you're welcome to create your own environments. You're welcome to work wherever you want, your computer, if you have an HPC account, if you have, access to other resources, go for it. But one of the things that I do want to offer is this idea of code spaces on GitHub. And I will be soliciting all of your GitHub usernames now that we're all here to add you to this so that you can find everything. But one of the things that GitHub offers is this code space idea, which is a virtual machine that I set up with an environment pre-installed. So you can click this when you it's like cloning a repo, but instead of going local, you hit code spaces, and then you can open it, and it builds the environment. So it has, oh, I think I forgot. Oh, it will load you into a cloud-based VS Code instance where you'll have access to all of the slides and notebooks and stuff. It's going to take longer than we have for class. So you'll be able to run all of your code here. I'll make sure that at least most of it we can do in this class in the code spaces. When we get to some of the deep learning stuff, we'll probably transition to some collab things, but I'll put the links to notebooks so that we can use GPUs and so forth. And we haven't even talked about GPUs or any of that, but we'll get there when we talk about deep learning.
Is this set up the environment on your computer locally, or is it?
It's all cloud-based. Yeah. Yeah. So it does. The first time you do it, it takes like 5-10 minutes. So it's eventually, like all the files and stuff will pop up, and you'll get like a Conda environment that it has all of the software for the class pre-installed. But I'll also at some point show you how to do it yourself if you want. Cool. All right. Let's get you out of here then.